Hello and welcome to Positive Physics. Today we're looking at lenses, and if you watch the refraction video you'll see at the end that I looked at what happened when you shone three beams of light through three different beakers, one with air, one with water and one with oil, and that as you changed the material within that beaker you had a lens effect, and the refraction that occurred of the light as it went into the different more dense medium made the light rays focus to a point. And that's how lenses work, and all we do is change either the material within the lens, so we change something called its refractive index, which isn't something you need to know for GCSE and you'll do at A-level physics, but it's basically telling us how much that light is bent or changed direction when it travels through that material. And we also do it by changing the surface of the lens and its surface shape. So the more curved it is, so I demonstrated it with like a circular beaker, the greater the focusing power of the lens. So a fatter, wider lens will focus the light closer to it than a slimmer, thinner lens. But there are a few features that we need to know about lenses, and there's two types. There's convex, and they are converging, so bringing the light rays together. And concave, diverging, so that means spreading the light out. And they have different uses, but we can start by labelling some common features. And one of them is this axis which goes straight through the centre of the lens. This is called the principal axis. Okay, and you'll need to know that. Alright, the principal axis is basically straight through the centre of the lens, and any light that travels along the principal axis will not be refracted by the lens. And that's because the angle of incidence of that light, if I draw you a little diagram up here, there's our surface of the lens. Our light is travelling in so that its angle of incidence is 90 degrees to the surface. So it will just continue on into the material undeviated. There'll be no refraction effect. So that's our principal axis. Any light along the principal axis goes straight through the lens. Remember, that's a really good point and a good thing to know. If we then take more light that comes as if it's coming from a very, very long way away, so we tend to talk of it coming from an infinite source. So if you've used lenses in the classroom, you might have used them to focus the light from a window onto a wall to get a little image of a wall. And that's because the light is a long way away. So what we've got here, we've got our light coming from a long way away, and the light is refracted as it goes into the lens, refracted again as it comes out of the lens, and focused to a point. Now, when you're drawing ray diagrams, if you were drawing something like this, you might want to show that the refraction had happened twice, but you don't have to, okay? So we've got this focusing of light, but there's a few other things that we need to label. This point here is given the letter F, and it is called the focal point, sometimes called the principal focus. Okay, always with its principal focus, focal point. Okay, it's not generally just the focus. All right, so there's the focal point, and then we take a measurement from the centre of the lens. Let me do this. Let me draw an imaginary centre line down the lens. This distance here from the centre of the lens to the focal point is called the focal length. Okay, so we've got our principal axis, our focal point where the rays will be focused, and our focal length, the distance from the centre of the lens to the focal point. Okay, now concave is a diverging lens, and so that means that when the rays of light come through, they're going to be spread out. There's not going to be this focal point where the rays come together for our concave diverging lens. In the same way though, the light that comes along the principal axis will not be changed. But let's do two more rays coming from, as if they've come from a distant object. Okay, and they are refracted as they enter the lens, and then, so let's do that both sides, and then refracted again as they leave. And what you find is that the rays, you just see me do a little construction mark there, bit of cheating, okay, the rays are spread out, okay, and what happens is it's as if the light came from this point. So now I'm drawing virtual rays, they're not real rays, so therefore I draw them with a dotted line. It's as if they came from this point here. Well, that is, I'll put it in red so that you can see it differently, that is also F, okay, that is the focal point of the concave or diverging lens. It's as if the rays came from that point. Now I've forgotten to put my arrows on my incident rays. I would tell myself off if I was in class. Right, so got our focal point, principal axis, and again, as with our concave lens, we also have our focal length, the distance from the centre of the lens to the focal point. Okay, so we've got converging and diverging. Now when you come to your exams, you might be asked to draw some ray diagrams, and the way that they might not say to you it's a converging lens or it's a diverging lens, but on the diagram what they will have drawn is something like this, so an arrow, or one with its arrow ends upside down. And the way to remember that this is the convex or converging and this is the diverging is to think about the shape of the lens. So here you can imagine those arrows following round, and you can fill it in. You've got a convex lens, a converging lens, okay? And here likewise you can imagine the shape of the lens coming in like that, so it's thinner at the middle and fatter at the bottom, and that is our diverging lens. All right, so that's how I remember, and hopefully that will help you too. Now, ray diagrams, and I've written don't panic, because everybody, I don't know whether it's the same where you go to school, but whenever I teach this, everyone goes, oh, I can't do this, it's too difficult. It really isn't. You just need to not panic, and then there's two, maybe three things to remember, apart from the fact that you need a ruler and a sharp pencil. Do you remember that I said that rays that came along the principal axis of the lens just carried on straight through the centre of the lens? Well, we are going to take one ray from the top of our object. This is our object here. We always show it as an arrow so that we can put the arrowhead to show which way up it is to see whether it's been inverted. So the first thing with any ray diagram for lenses is to draw that ray of light that goes straight through the centre of the lens and carries on out the other side unchanged. So that's your first ray. That's the simplest ray. The other thing we showed with the diagrams before was that light that came from a long distance away, okay, so one of the rays of light will come and meet the lens in the centre of the lens as if it's parallel to the principal axis. Now from the diagrams that we've done before, let's have a quick look. Where does that light ray go, the one that came up? Well, it's focused through the focal point. So that's what we need to do with this ray. So we draw from it through the focal point, and those two rays will cross. Okay, so I'm just putting my arrows on my rays. Where they cross is where the image of that point is going to be. So I can draw in my image like that. Okay, so there's my image. Now what can we say about our image? Well, we can say that where I've put this object, 2f just means twice the focal length. Okay, twice the focal length away. This image is upside down, so it is inverted. Okay, it's actually about the same size, or it should be had I drawn my diagram precisely, and it is real. These are all real rays, solid lines, real rays, so it is where real rays meet. Okay, so these three things are the ways that we describe the image produced by a lens. Is it upright or inverted? Is it diminished, that means made smaller, the same size, or enlarged, made bigger? Is it real or is it virtual? And real you can think of as, can I put it on a screen? But a better way of answering that question in an exam is to say it's where real rays meet. Or if it's a virtual image, it's where virtual rays meet. So here we've got a different situation where, and we're still not panicking, remember, where we've got our object closer to the lens than the focal length. And something a bit different happens in this case. But we're not panicking. We are drawing our first ray straight through the centre of the lens. And it continues on. And we're drawing our second ray parallel to the principal axis. Let's put our arrows there. And we're focusing it through the focal point. Now we see we've got a problem. They're not coming together like here. They're not going to have a real image. So what do we get? Well, we get a virtual image. And this is actually an example of a convex lens being used as a magnifying glass. So if you're an avid bug watcher and you get your magnifying glass out, or perhaps you're a Sherlock Holmes fan and you've got your magnifying glass out to look at bugs, fingerprints, okay, you are using a convex lens as a magnifying glass. And what we have here is that we extend our rays of light. So now they are virtual. We can't see this. We would be looking, if I put a little eye in, trying to do lots of things at once here. There's a little eye. We're looking along this point, and our brain, our clever old brain that says, you can't fool me, light travels in straight lines, I know where it's come from. It's come from here. Tells us that our image is here. Now I haven't drawn that the same, but there you go. Make it the same as my object, so it looks the same. So this image, which is still with a convex lens, is not inverted anymore. It is upright. It's not the same size anymore. It is enlarged. But it's also not real anymore, because now it is where virtual rays meet, so it is virtual. And I'm going to put in brackets where virtual rays meet. Now, this arrow here is representing our lens, and it's representing the centre of the lens. So whereas in the previous diagram I showed the light being refracted at the entrance and the exit, what we do when we draw these ray diagrams is we make life a lot simpler for ourselves, and we assume that that refraction happens in the middle of the lens at one point and it's focused through the focal point. Okay. Now sometimes you might get asked to explain what happens when you move this object either towards or away from the lens. So obviously if it's going closer than the focal point, so I must just put on there that that's my object and that's my image. If it's close than the focal point, then it's enlarged, it's virtual, and it is upright. If it's at twice the focal point, it's inverted, the same size and real. But what about in between? So rather than spending time drawing all these now, I've done them for you. So if we move our object closer to the focal point, but not at the focal point or between the focal point and the lens, oh look, spotted an error, quick, before you all spot. Right, you see that the object is now, the image is here. And so when we are between F and 2F, the image is inverted, it is enlarged, and it is real again. It's where those real rays meet. When it's greater than 2F, our image is inverted, it is diminished, it's got smaller, and it is also real. Now the only funny position is at F, where the image actually disappears. It's infinite and you can't see it, but you don't need to worry about that. Okay, so make sure that you remember, or you try and remember, how moving that image the object changes the image height. So a long way away, it's small, inverted, real. Getting closer, it becomes the same size at 2F, still inverted and real. It gets bigger and bigger and bigger as you go towards F, but still inverted and real. And then when it goes the other side of F and is closer to the lens than the focal point, it becomes virtual and enlarged, okay, and upright. Right, so that's convex lenses, and hopefully now you're at a point where you're not panicking. So we're going to do ray diagrams with diverging lenses, the concave lenses, and I'm saying still don't panic, okay? Let's apply what we've just learned. So here we have a diverging lens. It's got a focal point. Remember, that's the point where the rays appear to have come from. And we know that a ray that comes from that point on our object will go straight through the centre of our lens, undeflected, and we've got one ray already. So often in a lot of questions, that gives you a mark. Our second ray goes parallel to our principal axis, and this is the bit where it's slightly different. Because it's a diverging lens, and use the shape of the arrow there to remind you, this ray is going to spread out like that. It's not going to be focused into the focal point, it's going to spread out. And it's as if it came from the focal point. So we can put that there and draw our ray. Now that ray doesn't meet this one. So again, we extend it back or extrapolate it back. That's the real scientific way of saying it. Okay, with our virtual ray, and we get a point where our virtual ray and our real ray meet, and that is where our image is formed. So here we have our object and our image. And we can see that our image is, well, it's upright, it is diminished, and it is virtual. So if you are looking through a concave lens, things will appear to be smaller. And I've got a little example of this. I'm hoping this is going to work. Okay. So if I move, these are my old glasses. you can see that the size of the image has been made smaller by my glasses. They're diverging lenses, and it's not real. It's not a real image. You're seeing through the lens. You can also, though, can you see the diffraction going on of the light rays coming through that lens? So it looks like that line that I've drawn is completely bent. In fact, if I put it there, you can see two, just about, you can see two of the arrows. Can I do it here maybe? There you go, two arrows. Okay, so that's a diverging lens. The image is smaller and it is upright and it is virtual. One final thing for lenses is the magnification of the lens. So there's an equation which is that the image height divided by the object height is the magnification. So if your image height is much bigger than your object height, you'll have an integer magnification. If your image is smaller than your object height, you'll have a decimal. Okay. It can also be calculated by image distance divided by object distance, but you're not often asked to do both, but you might be asked to look at some data. However, one thing to note, if a question asks for magnification, you don't need the x, the times. You know, we talk about a 3 times lens or a 100 times lens when you're looking particularly in biology down a microscope. So your magnification is if your image height was 3 centimetres and your object height was 1 centimetre, you would simply write that the magnification was 3. Okay, that's all for lenses. I hope that was helpful. Bye for now.